Hello everybody. Let's look at question 1 for work, energy and power. Now work is defined as the work done by a force is the product of a force and a displacement in the direction of a force. So realize that this is actually a dot product or scalar product of vectors, and it can have positive or negative values. So work and energy are scalar quantities and have no direction, but they can have positive or negative values. The angle theta represents the angle between the force and the direction of the displacement. So it's actually the force and the projection of the force on the displacement. So this would actually be FG cos theta, the value. Okay, so this is the work done in the direction of the force. Now, let's talk about the work done by a person lowering his hand, lowering a weight in his hand. So over here we have a person who is holding up a box, and then this person now lowers the box until it's over here. The question is the work that the person done positive or negative? So let's look carefully at how the forces act on the box. So here is the box at first, and this is the normal force by person on the box. This is of course the weight of the box. Now, then the box moves down. This is the box moves down because the person's hand, this is the person's hand, is supporting the box. So the normal force by the person is continuing to act upwards, right? So the normal force acts upwards, but the distance moved by the box is downwards. So because the normal force and distance are in opposite direction, all right? So therefore, the when you start to do the calculation, N is in this direction and D is in this direction, and the angle between N and D is 180 degrees. So ND cos 180 degrees is equals to minus ND. This means that when lowering a weight, the work done by a person is negative. Now, what does this actually mean? When you lowered a weight, the work done by the person is negative. Now, remember that negative work done tends to slow down a body. Now, if the person was not supporting the box, then the box would fall freely. So what this means is that actually when lowering a crate to the ground, you're actually trying to slow it down. And because you're trying to slow it down by lowering it slowly, that's why your work done is negative. So that's a physical understanding of what's the meaning of negative work when lowering a box. Okay? Now, when a hammer strikes a horizontal nail into a vertical wall, the work done on the nail is positive, while the work done on the hammer is negative. Let's take a look at this situation where we have a vertical wall and then we have a nail that's sticking out here, right? And then we have a hammer. The hammer is going in this direction. Okay, so when the hammer hits the nail, there will be a normal force by the hammer into the wall, and then there will be a normal force by the nail on the hammer. However, what happens is that the nail goes into the wall like this. So that means that there is a distance move by the nail, and there's also a distance move by the hammer. The hammer also moves a certain distance down. Because the hammer is touching the nail, so there is the same distance for both usually. All right. So what is the work done on the nail and the work done on the hammer? Let's take a look at the nail. For the nail, it has a hammer force acting on it and then a distance move into the wall. But for the hammer, it has a nail force acting on it and the distance move is in this direction. So this means that on the nail, the work done on the nail is positive. But the work done on the hammer is negative. Now, we can easily see that this is true because if you think about it from a physics point of view, the hammer is trying to speed up the nail, but the nail is trying to slow down the hammer. So basically, if you try to speed up an object and you push in that direction, the work that you do should be positive. And if you're trying to slow down an object and you push against it while it's going forward, then the work done on the object is negative. So the answer for this is true. The direction of movement of the nail is in the same direction of the force on the nail. The force on the hammer, however, is opposite to the direction of movement of the hammer. And this is question 1. Let's take a look at question 2. Now, the concept for this question is that the work done by a force is the area under the force displacement graph, and that there can be both positive and negative areas. So the figure below shows the variation with distance of the force applied to an object determine the total work done. The answer is that you must find the area under the force distance graph. Okay, so this will be a negative area, will be negative work done, and the one above will be a positive area. So this is positive work done. Now adding them up all together, the work done will be positive 4 joules. Now where did the work done go? This tends to speed up the object by increasing its KE. And that's it for question 2. Let's take a look at question 3. In question 3, the main concept is that work can also be done by the gravitational force. When an object falls down, it falls down because the weight is pulling it down. So the weight speeds up the object. That means to say, when an object is moving downwards, weight actually does positive work on the object. Now what happens when weight does work on the object? Now what happens is that the weight takes GPE from the object and converts it into the KE of the object. And vice versa. When an object is thrown upwards, it slows down because the weight is slowing it down. So the weight has taken the KE of the object that's going upwards and changed it to GPE. Now let's take a look at this car. This car is moving downwards. It's a 3 kg car down a 15-degree slope as shown. Let's calculate the change in gravitational potential energy of the cart. Now, because the cart is moving to a lower place, so basically the height change is negative. And so the cart actually loses GPE. How do we calculate the loss in GPE? The change in the GPE will be equals to the mg multiplied by the change in height. That will be 3 times 9.81 multiplied by the change in height will be negative 20 sine 15. And this will give us negative 150 joules. Now, take the work done by gravitational force on the cart. Since the gravitational force converts GPE into KE, so using this idea, the gravitational force therefore does the 150 joules of work. Because the gravitational force is actually taking from the GPE and trying to convert it into the KE of the cart. So take the relationship between the work done by the gravitational force on the cart and the cart's gravitational potential energy. So the work done by the gravitational force on the cart equals to the loss in its gravitational potential energy. So if you wanted to write it in math, you can say that the work done by the gravitational force is equals to the negative of the change of the GPE. And that's question 3. Let's take a look at question 4. Now, what happens in question 4 is that a spring is being stretched by a force. When you apply a force to the spring actually goes longer, alright? So this is what happens to the spring. The spring grows longer by a distance x. So you can see that when you apply a force and then the spring moves in a certain direction, actually there's going to be a work done. However, there is a complication. Because the force that is needed to the spring keeps increasing as the spring extends. due to Hooke's law. So this is a graph showing the force and the extension of the spring. Can you see that this is actually a work done graph? Because the extension is the kind of distance that is moved. So the area under the graph is the work done by the force. And the work done by the force to stretch the spring is then stored as energy inside the spring. So let's take a look at the work done to stretch the spring, okay? When the spring's extension is E, the elastic potential stored in the spring is also E. So this area under the graph is E. When the extension increases from E to 2E, right, what is the change in this axis, in this area? Now, first we got to figure out how big is this new area, okay? We can do that by doing a scale drawing. So let's say I cut like that. Okay, you can see immediately that this area is also E, okay? And then let's say I draw a diagonal like that, and you can see that this area is also E. And by doing a mirror image, this area is also E. So the new elastic potential energy is 4E, and the increase in EPE is this area here. The increase in the EPE is 3E. All right. So there are two concepts to be used in this question. The first concept is that the energy stored in the spring is the area under the fx graph. The second thing is that the area under the fx graph can be analyzed, by drawing similar triangles. So it saves you a lot of time in the exam. And that's question 4. Now let's take a look at question 5. The concept in this question is the formula for the conservation of mechanical energy. So all we need to do is to work out what is the KE and GPE at every point that's interesting to us. So we'll work out the KE at point A first, which is 14.4 joules. And we can do the same for the GPE at point A, the KE at point B, and the GPE at point B. Now, once you've done that, these are all the values that you get. And you can see that the KE has increased, but the GPE has decreased. So what about part A? Let's calculate the loss in GPE. So the loss in GPE will be equals to 39.2 minus 25.5, which is 13.7 joules. What about the gain in KE? The gain in KE would be 25.6 minus 14.4, which is 11.2 joules. Now, do you see that there is actually air resistance acting on the ball because the loss in the GPE is not equal to the gain in KE? So what is the work done by the air resistance? The work done by air resistance can be found in two ways. All right, this is actually the W net. It can be found by 13.7 minus 11.2, which is going to give us 1.5 joules. Okay, well, actually it's negative 1.5 joules. All right, so it's 11.2 minus 13.7. It's a negative work done because it's reducing the KE of the ball. Or you can use this formula up here to work out that W net equals to, and then you subtract everything over there, you get minus 1.5 joules. So it's a negative work done once again because air resistance is tending to make the object lose kinetic energy. So it's a negative work done. Now let's take a look at question 6. This is a challenging question, so let's do it together. Bungee jumping can be analyzed at different points. At point A, the bungee jumper starts falling from rest. So let's imagine there's a bungee jumper over here, and he has a bungee cord that is 16 meters long. So it's a 16-meter long cord. So when he starts falling from rest over here, he has got maximum GPE, but the KE is 0. So it's a maximum GPE, but 0 KE, and also 0 BPE. Now, So this is point A. At point B, the bungee jumper is in free fall. So over here, the bungee jumper is still falling. All right. So over here, the GPE is lower. Okay, so it's lower GPE, but it has some KE, and then it has 0 EPE. So this is point B. Now, somewhere along the line, all right, the cord attached to the bungee jumper just becomes taut. That means it's 16 meters long, all right? Now, the bungee jumper will have lower GPE. It will have some KE, higher KE, and then it has still got 0 EPE because the spring hasn't started to stretch yet. Okay, so this is point C. Now, then after that, the bungee jumper will extend. So this is going to be 16 plus X meters. All right, so this is 16 meters plus X. So over here, at point D, the bungee jumper is at maximum speed. Okay, so how do we get maximum speed? The bungee jumper is at maximum speed when the tension of the cord is equals to the weight. So when the tension equals to the weight of the bungee jumper, that is at maximum speed, just like how terminal velocity works as well. So over here, it has still got lower GPE, even lower GPE. It has maximum KE, and then it has some EPE. Now, at point E, the bungee jumper comes to an instantaneous stop. Okay, so at this point in time, it's 16 plus X plus Y. Okay, we don't know how much, or maybe you just put 16 plus Y. We don't know how far it is right now, okay? But this is where the bungee jumper reaches a stop. So after that, he's going to bounce back up. So over here, we have the lowest or 0 GPE, right? And then we have the 0 KE, and then we have the maximum EPE. Okay, so just take a look at this diagram, all right, and then take a look at how the EPE changes. Now, the most important thing to note is that the bungee jumper reaches maximum speed when the tension in the cord is the same as the weight. This is just like how any terminal velocity works. You know, when air resistance is equal to the weight, then the object has reached the maximum speed. So in this case, the bungee jumper is being pulled by the string. So when tension equals to weight, that's when the bungee jumper has reached the maximum speed. Okay, so have you remembered all this stuff? Yeah, I hope you have. And it might be a good idea to copy down the diagram as well so that you can remember it. Now let's take a look at the diagram over here. Okay, label the graphs that represents kinetic energy, gravitational potential energy, and elastic potential energy. So I'm going to put this diagram over here. All right, then we can figure out which energies go up and down. Now notice that at point E, there's going to be 0 GPE, 0 KE, and maximum EPE. So this means that this graph over here must be the EPE graph. Okay, so this is the elastic potential energy graph. And this elastic potential energy graph is maximum at point E. Okay. Now, what about over here? Over here, the bungee jumper has just started jumping, so this must be point A. Okay. Now, when does the bungee jumper just start to have EPE increasing? Now, the bungee jumpers just starts to have EPE increasing at point C. Okay, let me just circle this over. So at point C, okay, you can see that that is starting to have EPE. So this must be point C over here. That means somewhere along this line, we don't know where. This is point B. Okay. Now let's take a look at point D. Now at point D, you're going to have maximum KE. Okay, at point D, you're going to have maximum KE. So the KE over here is maximum at point D. So this graph must be KE, and this graph must be GPE. Okay, so let's take a look at how the graph works and compare it with your drawing from before. Just let me try to get this drawing over there. Okay, now, so at point A, the bungee jumper just steps off the platform. At point B, he is falling. At point C, the EPE just starts to increase because the string is stretched to, let's say, 16 meters, which I made it up myself. Okay, at point D, that's when you have maximum KE, right? Then at point E, that's when the person has stopped the most, and then he's going to come back. Now, by considering the forces acting on the bungee jumper, explain why the speed is maximum at point D. Okay, so at point D, before point D, the tension is less than the weight, and the bungee jumper continues to accelerate downwards. After point G, the tension is greater than the weight, and the bungee jumper starts to slow down. Hence, the speed of the bungee jumper is greatest at G. Okay, so this is the tension of the bungee jumper, and this is the weight. Okay, before point D, the tension is smaller than the weight. So the bungee jumper will keep going faster. After point D, the tension is larger than the weight. Okay, so the bungee jumper will slow down. So at point D, when the tension equals to the weight, the bungee jumper will be at maximum speed. And this is the bungee jump question 6.